All right, welcome back. Fluid mechanics, chapter 4. Failed on the quiz again, so I moved it to Wednesday, as you can see. So I'm going to build that quiz right after this lecture. I'm going to make it available Wednesday. Let me know if you have a problem taking it Wednesday. I'll give it to you a different day. So we need to get that done. It'll be over chapter 1 through 3. Okay, couple problems. Do it and upload it. I'm going to move into chapter 4. Keep moving forward. Chapter 4 is a pretty big chapter, a lot of concepts. So let's look at a few of them. And then there is a couple homework sets for you that's shown there on screen. Nope, not that way. Yeah, I get better down there on the 19th. Looks like it's out of chapter 4, 2, 5, and 6. So that means I need to cover Reynolds number. That's laminar and turbulent flow, and also conservation of mass, which is a cool concept, and then conservation of energy, which is another cool concept that we use in hydraulic and fluid powered systems. So this first part is very mechanical. I know not all of us are heading that direction, but that's just the way this class sets up. And then we move towards civil and more open flow systems. So patience with that. All right, I'm going to rotate you around and talk about Reynolds number. We don't have a lot of setup for Reynolds number. It's pretty kind of isolated in the structure of a pipe, because that's how most of our fluid power systems are, is in piping. So that's a round circle with a hole in the middle that we transmit fluid through. And what we want to understand is that there's two different kinds of flows. There's laminar and there's turbulent, right? Turbulent flow has much more loss of energy due to the turbulence. Laminar flow is a much better distribution of energy. We lose less. Unfortunately, most of our systems are turbulent when it comes to fluid power systems. So the equation to calculate it is pretty simple. It's shown on page 54. N sub R is Reynolds number. Large D is the diameter. And I'll try to be careful with my V. I'll just make a clean V for velocity. That's the upper symbol. And then this is like the Greek V, and I'll try to put like a little tail on it and kind of make it a little more curvy. For you, and that's the viscosity of water. So in a lot of cases, when we deal with fluid power, we use water as a reference point. So even though we may use other fluids, a lot of times they just show you this, right? The viscosity of water. So it's a huge range. If you have values up to 2000, so under 2000, those are typically going to be smooth or laminar water flow. And again, using the viscosity of water. If you're going to do oil or antifreeze or some other kind of fluid, air, then you're going to use the viscosity of that material, right? Above 10,000 indicates turbulent flow. So that's a huge range between 2 and 10. What's going on? Well, probably combinations of laminar and turbulent flow. So it's pretty big range and a basic estimate essentially on whether you have a laminar or turbulent flow. Okay, notice the units. This is the inside diameter of the pipe in feet. That's important, because that's what's going to work with the USCS system of average velocity in feet per second. And then the viscosity is feet squared per second in the US system. In the metric, it's going to be meters per second, and then meters squared per second for that. Okay? So just be really careful with your units and calculating the Reynolds number. So that's really just an equation that we need to kind of practice a little bit. I gave you one problem that's going to give you the velocity of water in a pipe and say, what do you think? Is it going to be below 2,000 and laminar, or above 10,000 and turbulent? So you'll be able to calculate that. Just keep your units straight for your Reynolds number. All right. So the next concept of this chapter starts into our conservation of mass and what we call energy head. So in fluid mechanics, we capture the energy of a system with the unit of feet, which is going to be very unusual for you. Like, it's very specific to fluid mechanics, but head is referred to as a height, and that there's some kind of energy up high, right? So the energy in foot-pounds, meaning that this weight is a certain amount of feet above us, okay? If it's 100 pounds and it's 10 feet up, then we have 100 times 10, that's 1,000 foot-pounds, okay? And if we divide by the pounds, we come back to the 10 feet that I just spoke about, right? So we can quantify energy in the unit of feet, and I'll show you that in a few different areas. We do it with potential energy, which is weight at a distance, weight up high, but we also can do it with kinetic energy and come up with a head in feet. So something moving, we can get the energy in feet. Velocity head. Something moving at a velocity can also give us energy in feet. So each one of these will categorize in the unit of feet, and that allows us to add energies, different kinds of energies together. Like potential energy, we can add to some kind of kinetic energy. We can add to some kind of velocity energy. We could add to some kind of pressure energy, right? And then we can also take away energy in the forms of loss, like head loss. That could be friction in a pipe. That could be heat that's created, right? That heat comes away from the energy. All right, so before we get into the full conservation of energy, they talk about conservation of mass. So conservation of mass says in a fluid system, and I'm going to say, okay, here's my fluid system, and it's going to be a 2-foot pipe. We'll just say that's the inside diameter, coming down to a 1-foot pipe, 1 foot diameter. Okay, and somewhere in here, right, is the transition from one to the other. If it's full of fluid, and that's what we do with our piping systems, is it's completely full. And if this fluid is moving at a velocity 1, what's it going to do here? Well, the conservation of mass says when you push this mass, and I'll just kind of draw a mass particle or a group of mass, right? When you push it at a velocity, that mass here, it has to travel at the same rate. In other words, this mass is going to create this mass, and obviously it's a smaller area, so this mass is going to have to accelerate, and the velocity will change from V1 to V2. That's called the conservation of mass, meaning if you move 100 pieces of mass here you have to be moving 100 pieces of mass. If the area gets smaller, A1, A2, then conservation of mass says, well, velocity 1 times area 1 has got to be equal to velocity 2 times area 2 on the mass level. Okay. So velocity is feet per second. Agreed. And area is feet squared, right? So feet per second times feet squared is what? That's feet cubed or cubic feet per second. Okay, if this was per minute, then it's cubic feet per minute. All right, it's called Q, the flow rate. That's what V1 times A1. Well, we could do the same thing over here and we get Q2 because the flow rate is gonna have to change in order for the conservation of mass to be equal, for this to be equal to this. So Q1 is not gonna equal Q2, it's gonna equal a different flow rate. The flow rate's gonna have to be that flow rate's gonna have to be absolutely the same. If we're transferring 1 cubic foot here, we have to transfer 1 cubic foot here. What changes is the velocity. So these will equal each other, they have to, right? But in order to do that, it's got to speed up. All right, that's the conservation of mass. Meaning that, okay, if we know what's going on here, we can calculate what's going on here because that mass change has got to be consistent. It's got to keep up. All right. So you can do these all the time if you know velocity 1 and you know area 1 and you know area 2 and you don't know velocity 2, you can just set up the equation like this and solve for velocity 2. And then of course, if you don't know any one of these variables and you know the other 3, you can solve for it. Or if you know Q, the flow rate, which is V times A. So Q, the flow rate is V times A. All right, so that's the conservation of mass. I think I gave you one of those problems. We use this all the time because we're constantly changing the diameter of pipe. We're trying to either speed up the velocity of the fluid or slow down the velocity of the fluid by opening it up. Okay. When pressure comes in, we'll have a P1 here, and then we'll have a P2 here, and we'll be like, wonder what's going on at the pressure level, right? So we'll get into that too. So the book talks about this conservation of mass and really just uses that equation to explain it, right? Then it goes into a very long derivation of the conservation of energy. You don't have to read through this. They get very technically complicated with this. They do talk about U, right? And potential energy and kinetic energy and kind of the terminology for it. But in the end, as you read through this derivation, it really is just a derivation. We're going to end up with the energy conservation equation. That's this, right? Now this, they couched it for a reservoir, so certain things will drop out. Like, for example, there's no P2, there's no P1 over here, there's P2 over here, right? So it's the way the energy equation sets up is this side is equal to this side because we have conservation of energy, okay? So the energy input into a system is equal to the energy that is output. We just have to figure out like what is the input and what is the output and what drops out. For example, on a reservoir is just an open body of water, right? That's a reservoir. P1, the pressure, the initial pressure of the reservoir is 0. There is no pressure right there, right? Down here, there's a pressure. So maybe, you know, if there was a output pipe or something that was our system, we might have a P2 that is involved, but P1 disappears for a reservoir. So just note that they kind of build their logic for the energy equation with a reservoir in mind. But let's go through each one. Remember that the way we add these energies is with what we call energy head. and that's feet. Right? And you can kind of go back to my, 100 pounds, 100 pounds at 10 feet, right? We know that the amount of available energy is 100 times 10 or 1,000 foot-pounds, because we take 10 feet times 100 pounds, right? But then if we say, okay, get rid of the weight, what's the head? The head is 10 feet. So that's 10 feet of potential energy, right? In the terms of feet. So we do that with each one of our energy states. And it boils down to that equation that I just showed you, right? So for example, if you have velocity going on, then velocity is going to be v squared. It could be v1 but it might also be v2. So you might have velocity on both sides, right? Divided by 2g. G is the gravitational constant, right? So for us in the US system, the gravitational constant is, I just want to use their terminology, so I was just going to look. I'd like to put in what they use for the unit of gravitational constant. So they use the number right here, 30, oops, sorry, you can't see it. In the US system, 32.2, that's the gravitational constant. And that's should be feet per second squared. So yeah, feet per second squared, 32.2 feet per second squared. All right, so let's see how this works. If we have a velocity and we want to know the energy head of it, let's say it's 20 feet per second, right? That's a velocity unit, and that is squared over 2 times 32.2 feet per second squared. Okay, so the unit analysis, I mean, we can get the number pretty easily. 20 divided by 2 is 10, and then divide by this, right? We're going to get a fairly small number. But let's look at the unit conversion. The unit conversion is, this is going to be what? Feet squared second squared? Yep, feet squared second squared there. Second squared in the denominator down here flips it up and it goes up on top. So those cross, right? And then feet squared and feet cross, and we're left with feet. Again, velocity head. This potential head. So potential energy head, velocity head. We could add these two together. That's how we do conservation of energy. We put every energy in the terms of feet. Okay, so the other ones are pressure. So pressure head is P divided by the specific weight. So if there's a pressure going on, we want to include that. There are head losses. So H1 is maybe the height, and this is the second height, because what happens is this is going to come over and subtract from H1, because this becomes an algebra problem when we do it, right? So your homework is just going to have you calculate these individual energies. Just the individual energies. You're not going to start adding them up or creating the equation yet. But the equation is coming and we'll start to use it. Okay. So velocity head, pressure head, potential energy head. Here's more velocity head. And then we'll have losses. We will add in friction losses, H sub F, and then we'll go through a derivation of trying to figure out like, oh, wonder how much the friction head loss is for this piping system. And that will lead us to the Moody diagram, but I'm not doing it yet. Not yet. Okay. So we'll just kind of enter into this. There's other losses, like there's entrance losses. So if we had, you know, a reservoir system like this, somehow this water enters into the pipe, there could be an entrance loss there. there could be an exit loss here. Okay, so there's a lot that can happen. We're just gonna take it in small steps and you're gonna do some individual energy analysis. All right, good luck with that. And I think you'll be fine with it. It's not too awfully difficult. Quiz on Wednesday. I'm gonna build that right now. And then I'll send you all an email so you know what's going on. And then I'll send you a reminder on Wednesday. So moving forward. Hope you had a great weekend and I'll talk to you again on Wednesday is my hope, maybe Thursday.